Is it going? There we go. Cool.
He's using AI. He's cheating.
Yeah, it is. I wonder what it used beforehand. Before that, like, could have had that for a little while. Alrighty. Cool. So he has a couple different problems for me to work today. There were two from the homework, I guess you just submitted, that he got a lot of questions on. So he asked me to work those as well. One's like conservation of mass. It's number 2 on the homework, and then number 3 on the homework was like conservation of the momentum problem. So, and then there's one from last week that he wanted me to work as well. That I didn't get to.
Can I just ask you something before you start?
Yeah.
Can we get to 2 and 3? Just for like, I feel like this is the general consensus of the class. Like the math, I don't feel like was hard for any of us for that, but like the logic in approaching the problem is like where I think we were struggling the most. So if you could kind of like explain to us like in depth, like your logic of how you're approaching it, that would be awesome.
Yeah, I can do it. Yeah. Of course. That reminds me, I better get my notes out so I actually can reference those.
I'm sure you got a lot going on. Hey, Ray, this isn't exactly at the top of your list.
Well, I prepped for it today, but I've been doing other things, over the weekend and stuff. Yeah. So.
How the exams been going?
Good. I only have one class, and it's basically just differential equations again. So it's not been anything. Yeah, it's not been anything new. It's just been really good. It's Dr. Lusk. Have you had him before? Dr. Lusk. Yeah. Yeah.
He's an awesome professor.
He's good. He's very good. Yeah, he's a cool guy.
He's funny too.
Yeah. Yeah, and his class has been like, of course, because of the hurricanes, like we missed so much class that he's like trying to catch up. But he's like, I'm not going to be able to. So, he's like, we're not going to speed up to double pace because that just wouldn't be fair. That's cool. Love him. But yeah, so whenever I get to that one, and wow, I didn't even know it was a feature. That's cool. Whenever I get to that one, then I'll like go more into detail about the thoughts of it. So, yeah. Okay, so this is similar to what we did last week. Same type of problem, and we have this like U-bend that is decreasing in radius. Steady flow, 20 degrees Celsius of standard temperature. We know the pressure and diameter and velocity at the beginning of the pipe flow, and we know the pressure and the diameter at the end at section 2. And then so it says neglecting the weight of the pipe, the bend, and the water. We want to estimate what the force is in all those bolts that's holding that system steady, holding it still. So I'll start by writing some givens here. So we got water, 20 degrees Celsius. So then you can read tables with that if you need to. We know we have our figure there that says that the ambient pressure is 100 kilopascals. And then we know that we have section 1 and section 2. Section 1 has a pressure of 350 kPa and a diameter of, I'm going to write it in meters. So 0.25 meters. And then a velocity of 2.2 meters per second. And then in the second section, we know we have a pressure of 120 kilopascals and a diameter of 8 centimeters. Okay. And then what we want to find is, I'm going to call it FB to be consistent with last week. I used FB as well for the force in the bolts. And yeah, we just want to find that. So did you have the same sort of question about these problems? Did you look at these from last week at all?
Yeah, no, we looked
Okay.
at this from last week, and I mean, these are kind of just like more simple, especially like with steady flow. I feel like the logic behind it isn't too bad.
Isn't too bad. Okay. Okay. Cool. Cool. So, yeah. So essentially, we've got that. The sum of our forces. The sum of our forces is equal to d dt integral over the control volume of rho v d volume plus the summation of m dot I vi for the outgoing flow minus summation m dot I vi for the incoming flow. But then because it's steady, we know this one goes to 0. And then we know we have 1. This is going to be section 2, because that's our only outgoing flow. And this is section 1, because it's the only ingoing flow. Okay, so what we can do here is we see that we know that m dot is going to be constant. M dot 1 equals m dot 2. So we can go ahead and solve for our v2. So if we know that m dot 1 equals m dot 2, then we can say that rho v1a1 equals rho v2a2. Density is consistent in this case. So then we can say that v2 is v1a1 over a2. And then that will give 108 kilograms per second. Wait, no, I'm sorry. I got ahead of myself. Yeah, okay. I got ahead of myself. We know that m dot is rho VA. So then if we say that this is rho V1A1, then we can solve for that, the value I just wrote up there. So this would be 998 kilograms per meter cubed times 2.2 meters per second times the area. All right, that is what gives you 108 kilograms per second. So then you could solve for your V2 the way that I had it up here, where you say m dot 1 equals m dot 2, and then solve it from there. Or the way that I did it in my notes is I just went ahead and wrote out another m dot equation and solved for V2 that way. So I had 108 kilograms per second is equal to 998 kilograms per meter cubed multiplied by V2 times pi 0.08 meters squared over 4. And then that will give a V2 of 21.5 meters per second. And then, so now what we can say is that since we know the sum of our forces is going to be this, MV for section 1 minus MV for section, or sorry, reverse that. MV for section 2 minus MV for section 1. Then we can sum forces in the x direction, since all this is in x direction flow. Say this is the positive x direction. And then say that's going to be equal to okay. So then we can say that we know that V1 is in the positive x direction, the flow, but V2, the vector, is in the negative x direction. So then for this guy, we can say that this is going to be m dot 1. I'm going to drop the vector sign and say this is going to be I'm going to say positive V1 minus m dot 2 negative V2. Okay. And then we have to figure out this force term here. And so that, if you sort of thought about the force for these bolts, it's going to be going back that way, resisting the force from the fluid. And so then this will be a negative force from the bolts. And then we have the pressure force from the section 1, which will be P1 gauge pressure times area 1 plus the gauge pressure from section 2 times area 2. And that is because both of those pressures act inward on the control volume. So they're both in positive direction. Okay. So okay. So then if we rewrite this, yeah. So if we rewrite this, then we can say that the bolt force is going to be equal to P1 gauge times A1 plus P2 gauge A2. And then, yeah. Did I do something wrong? What have I done? That's there. That comes over. I feel like I've done something wrong if I don't see what it is. That to be there. V1. Oh.
Yeah, I was gonna say you have to multiply by 4 unless you're taking all the forces of the bolts at once too, right?
Well, that's kind of what I'm doing.
Okay,
Yeah.
So you're taking it all at once, then you divide it by 4 and to find the individual bolt force.
Well, it just wants the total.
Oh, okay.
So I'm just saying that's the total FB. Yeah. FB, and then this is P1A1, and this is P2A2.
So the P is just like conceptually, is it just cutting it and pulling it away so we can see that? Because when it says gauge pressure is
Mhm.
P minus PATM.
Mhm. Right. Yeah.
Okay. And then wouldn't the P2A2 be negative in order to accommodate for the direction?
Of the flow. So it's positive because of the direction of the arrow. The flow direction is taken into account when we said that that this velocity here is negative. Yeah. So right. There is a direction associated with it, but that's because of how pressure is always acting in on that surface. And then the direction of the flow is taken care of with the velocity sign.
Yeah, sorry, the P1 and P2 is kind of confusing.
Okay. Yeah, sure.
Like how it's coming in.
Mm. That was confusing for me too. Yeah. You mean just why are they both going right? What's the reason for that?
Yeah.
Okay. Yeah. So that was confusing for me as well, and I had to ask Dr. Bassel to clarify that. I'll draw. Okay. So right, we have this control volume, looks kind of like that. But the pipe actually extends, right? Like that. So when we had, gone in there and cut through per se to make that control volume, the pressure here was always acting outwards. Because pressure is never going to like suck in, it's always going to be right. It's always pushing out. Right, exactly. So like when we cut that, the pressure is pushing in on the surface, not, yeah. Does that make sense? Okay. Yeah, because I had to have that explanation too from him to kind of know. And so that's why he said that then this flow direction is why the V2 is negative, but V1 is positive. And so that's accounting for if you had a pipe that was like maybe flowing, instead of doing a U bend, it did like an S shape or something, then your velocities would both be positive. But again, you know what I mean?
Yeah, because you'd be going back around, so it'd be coming out in the same direction as going in.
But your pressure would be negative in that case.
It would be.
Yeah.
It would be, yes.
But
Yeah.
they'd be acting in against each other.
Right.
The pressure is basically always going to be compressive.
Yeah. Exactly. Exactly. Yeah. It's always compressive. So, yeah. That's a good question, though, because, like I said, I had the exact same one. Okay. Let's see. So now, what the heck did I do? Yeah.
I think there's a lot more things that.
Oh, I see what I did. I think. So this guy. Yeah, I see what I did. Okay. So where have I? Let's see. So this was 2. I think I just wrote my equation down. Maybe reverse order on you on accident. Right. Well, yeah. So see here, I put. it is outlet in,
Okay.
but whenever I switch slides, I wrote it down as
Oh, you wrote it
1 and then
in
2.
and out. Okay.
So I flipped it around. Yeah, so really it should be this. I accidentally flipped them. Yeah, so it should be like that. Okay, that fixes it. So then if you move it over, then because those will both be negative terms. So when you move it over, then you add on m dot is consistent. So I'm just write just m dot, and then it'll be v1 plus v2. And that gets the signs correct. So, all right. So then P1 gauge is going to be 350,000 minus 100,000 to get the gauge pressure. And then we have the area. That's the first term. Then we have our second term, 120,000 minus 100,000. And those are pascals. Pascals. And we have pi 0.08 meters squared over 4. Our m dot was 108 kilograms per second. And then we have these two velocities. And at the end of the day, that's going to give you 14,931.98 newtons.
That's about what I thought it was going to be.
Question about the
Plus or minus 0.5%, right? Yeah.
gauge is T minus P to T, right?
Yes.
So why are we doing that? Is it because when we take the control volume, it's like in contact with the atmospheric air instead of just being a regular pressure that it would be in the pipe if it was just a continuous pipe?
So the reason you do it is to make your life easy.
Okay.
Yes. So it doesn't have anything to do with like the control volume is not like it's touching the atmosphere or it's not touching the atmosphere. It's not changing anything there. The reason that it makes your life easy is because there's this PATM acting on the pipe.
So it's creating a force.
Right.
I see.
Oh,
Okay.
It's
figured
creating a
out the
force.
equation by doing that.
Exactly. Because if you do gauge for PATM, it's 0. Right. Or if you engage pressure thinking, the atmosphere is 0. The reason it makes your life easy is because let's say you did have that force that's acting, horizontally, let's say, because we're going X direction. But then in order to turn that into a force, you'd have to know the area of that entire pipe.
Yeah, like the surface of it.
Right.
And then
Which
you
is just,
do it as like a
yeah.
distributed load over that or what?
Right. Exactly.
Okay,
Yeah. You'd have to know, I guess it wouldn't be distributed, but it would be, you'd have to know what's the
Or you just
projected
have to
area.
Oh, okay. So you
Yeah.
just calculate the pressure created from, or the force created from the pressure on the outside of the pipe.
Right.
Okay.
And so that area would be a projected area, which would just be complex to calculate. So if you just take it out of the equation by using gauge, then your life's a lot,
And
simpler.
then another thing I was gonna ask is when it says neglecting the bend, is
Mhm.
that like grouping just so I'm like understanding like the logic side of things? That's meaning that we're neglecting frictional forces and the forces it creates from having the height change? Because like bends obviously, like I know like in like HVAC at least, like if you have like a 45 or like a 60, like it's gonna affect the frictional forces and then the flow rate also, right? So is that what it's saying? Like what is all wrapped up in the neglecting the bend? I get the water weight, but
I think whatever
Yeah.
okay.
Yeah, I guess, yeah, I mean, that's a good point. I guess you're just kind of saying like everything's kind of weightless
It's like, yeah,
in a
it's
sense.
it's just wrapped up all into like one thing. So I want to make sure I knew like what it's
Yeah.
taking out.
I honestly, I don't know the exact reason. I'll ask if you want me to.
I can just ask myself.
Okay. That sounds good. Yeah.
Not gonna waste your time.
Yeah, well, no, you're good. That's why I'm here. But yeah, I mean, I don't know the exact reasoning behind it, but if you're just assuming that there's no weight, it's like of the water moving through there and stuff, then it just makes it simpler. Yeah, that's a good question though. I guess you're right. The water would have like some sort of friction flow,
Yeah,
you
so I
know.
know like when a vent, like when you approach a vent, at least like HVAC or like air, like the friction increases significantly. Like when you're like in a
Mhm.
vent type stuff.
Yeah,
Just
Yeah.
curious.
that'd be a good question for him for sure. For sure. He's always telling me how y'all have really good questions, which is good. So
So what is the prohibited?
no, he really does think very highly of y'all.
When in the first week of class, he's like, hey, I might have to go to save a nuclear reactor.
Oh, yeah, that was very good.
Yeah. I've got a picture somewhere of us dressed up. I'll have to show you.
That's awesome.
Yeah. Okay. So let's see. Number 2. So this okay, so I'll explain my reasoning with this one.
Sorry, it doesn't stop it blowing. Can make that as your t-shirt. I'm ready. Have a t-shirt. I am drinking. I'm smoking because I'm drinking. I'm drinking because I'm smoking. What did you say it was? Science doesn't suck it blowing.
Okay. So I guess y'all have all seen this one before, right? Because it's from your homework. But so we have the cylinder that is 6 feet or 6 meters tall and 2 meters in diameter. And we know that it has an initial pressure of 2 megapascals. We know that we have a valve that opens, letting air out. So we have this like M dot out type thing from a valve. And then we know that the pressure inside is changing at a rate of M dot equals to 4 times 10 to the negative 6 times pressure. And that's kilograms per second. And then, yes, we want to assume that we have a temperature that's constant of 20 Celsius. And we want to find an equation for the air pressure in the tank with respect to time. So I'll say P of T.
I was just assuming it's heat pressure.
Yes. Yeah. Well, what do you mean? Oh, this P here? Yeah, because I think it says P is the air pressure right there. So it does clarify. Yes. Yeah, exactly.
No, it's actually the first pressure tank that isn't it's a balloon.
He also made an assumption with this problem, or there's an assumption that you take, is that like with regards to density. Well, it's one that we would always assume is probably the case, but that in real life it might not be, you know. But like if you took 2 different points, right?
So it doesn't. That's what he's talking about, where it doesn't change with position, but it changes with time, right?
Exactly. Your density as you let the air out will change, but within the tank at a certain second, it's going to be consistent all over the tank. So yeah, so density is a function of time, not space. So that's the yeah. So that's the trick with that. So Yeah, I think that's all the information we need so far. So then, okay, so when I look at this, we're gonna use conservation of mass for this. The reason is because we're not really dealing with any forces here. We're just dealing with like, I mean, you might think pressure, force and pressure, but we're thinking about we have a certain amount of mass. We're letting mass out of the system. Excuse me. And then that's going to change our pressure. But we're not really dealing with like forces per se, like a flow, or he's not stating that there are any forces acting on the system necessarily. He's just saying we have this system with mass, we're letting mass out, and so then how is that going to change pressure with respect to time? So that's kind of how maybe you can think about going with the conservation of mass first. So we're going to use conservation of mass here. And then that equation looks like d over dt integral over the control volume of rho d volume plus the summation of m dot out minus the summation of m dot in. And that's going to be equal to 0. Okay. So we know that we just have the one valve letting air out, right? Mm-hmm. And so then this guy is 0 because there's no inlet. And so then what that gives us is that this term is our only outlet, and it's equal to 4 times 10 to the negative 6 p. That whole term there. Because that's what's given as the rate of air loss from this tank.
Can I ask you one question?
Mm-hmm.
Do you use PV equals MRT at all for the solution?
Yes.
Okay.
You do. Yes.
Okay.
But we're going to use it as P equals to rho RT.
Yeah.
Yeah. Okay. Yes, you will.
Sweet. Yeah, but it's okay because we wrote it down, so that's all.
I mean, you could do PV equals NRT, but just extra steps.
We did like m dot, and then it was d over dt on the other side.
M dot d over t.
For sure. Yeah. Probably 6.
There goes 3% of my grade.
Well, you're saying you put the m dot, you moved it over?
Yeah.
You had the
like p equals mrt, m rt over,
Mm-hmm.
and then we did like times dt, d over dt on both sides is dm over dt is equal to, it's probably wrong.
Equals to what?
dm over dt equals dt over dt.
Yeah, times probably p over rt.
I see. I see. Okay. I think you're really close to what you did. I'll show you here as we derive this. I'll show you, but I think you're really close. So we know that this discussion of the density is time dependent, but not spatially dependent. Means that we can pull it out of the volume integral. So we can say d. I don't know why I wrote these as curly, but we're gonna do that. So we have ddt rho integral control volume d volume is equal to negative 4 times 10 to the negative 6p. So then this will become d rho dt. And if we integrate dv, we get just volume, right? Mm-hmm. So that'd be volume. And this is going to be this value. But remember, that is just to answer your question. That's just m dot. That's m dot out, right? Just to clarify that. So then, yeah. So then what we can say is that d rho dt is going to be equal to -4 times 10 to the -6 times, now this is rho RT, just using ideal gas law there. And we divide that by the volume, which is going to be pi over 4, 2 meters squared times 6 meters. And so then that is going to give, and this is in kilograms per second, this term here. So then that is going to give, okay, I can't do this. Once I hit that last, like, however much that is, it won't let me write anymore. So then this will be d rho dt is equal to negative 0.0178. That's what that whole thing right there, if you plug in R is equal to 287 and T is 20 plus 273.15 or 293.15, then that is going to give you that's going to give you that coefficient in a row. Okay. So then if we do separation variables, then we can say that d rho over rho is that coefficient multiplied by dt, integrate both sides, and say natural log of rho from rho naught to rho as a function of time is equal to that. And so then we can say this is the natural log of rho t minus the natural log of rho naught. And so this would be rewritten as like that. And then we can say that we take the exponential of that. So we can say that rho t is equal to rho naught e to the exponent of that.
We got the same exponential, but we had p is equal to p naught e to the same thing.
So you just have a p there? Okay.
I feel like that maybe will.
You're really close. Because the next step I'm going to do is I'm going to say that this guy, if you say that p is rho RT like we did earlier, then you can say that rho is equal to p over RT. So then you can say that pressure with respect to time divided by RT is equal to rho naught E.
So when we multiply it over, would that just be p naught?
It would be. Yeah.
So we got
It will be. Yeah. So I guess you did it just different way. But
I think we got it.
do you have a question?
No.
Oh,
Mine was,
okay.
mine was like close, but my exponential was positive.
Oh, okay. Okay.
This question was just.
Yeah.
I mean, he didn't do like anything with ideal gas law, so
Hmm.
he was trying to do it the way he did it in class, and it wasn't.
Yeah, but that's our fault. Well, it is. I mean, we've done classes with that equation.
Name 8 classes we've done that before. We went to 25.
25.
It is a pretty involved question. It is, yeah. Because you have to recognize conservation of mass, write that out, fill in all your assumptions, whatever, what you know, and then you've got to go through the calculus and derivation and doing the ideal gas law conversions. And
I mean, it's not bad
Yeah.
once you make the connection. Honestly,
Right,
the hardest
right.
part is making the connection with like D equals rho RT, and then or using the.
And for our solution, so we do the P naught, but we did P gauge. That
P
gives us-
gauge.
He gives us absolute pressure.
Okay. Okay, so he gives you.
Or should we be the absolute pressure?
I mean, I guess. So, like in the previous problem, we used gauge pressure to simplify the calculations a little bit. I mean, I think in this case, as long as you denote that that's gauge pressure and that's also gauge pressure, you know, I don't think that would change anything. Would it?
If you do it on both sides, it shouldn't,
Mhm.
because it's the same as like subtracting or adding something for both sides of the equation, right?
We can multiply it to an exponential.
Yeah, the multiplication I think might mess that up. But if you started with gauge pressure, I mean, he just denoted absolute pressure. So because we're not trying to make a simplification because of forces, I think that you can just use absolute and just carry it through that way. Yeah. But that is confusing though. It's like why in one case use gauge, in another case use absolute, and
I think
Yeah.
it's just the logic behind these problems that's like interesting. It reminds me a lot of like dynamics,
Mhm.
like how you have to approach them.
That's why I always do this like given find That's why I always do this given find solution type thing. Because if I write down everything I know and kind of like conceptualize it, read it a couple times, and then like draw a picture or write down the fundamental equations, I can start to think about like how it kind of starts to fit together.
That's exactly
And then-
what I do too.
Yeah.
The only difference is like I have to write like all the equations together.
Mhm.
If I have them at different spots on the page, I just like can't make those connections between.
Mhm. Yeah, I mean, everyone's got a different process. I was always the person who was like last to leave an exam because I would sit there and like take the first couple minutes just to conceptualize what was going on and then actually work the problem after that. So I think the only thing I haven't done yet is this guy is 2 megapascals. So you can plug that in since that's given. Or if you wanted it to be pascals, then this could be 2 times 10 to the 6th.
I mean, as long as we don't become professional engineers, we don't sign off on the project. So it's just government. Our mistakes are our boss's problem.
Okay. Any other questions on that one? Then we just have the one more problem. And so in this one, we have a fluid flow that hits a wall or a plate or something like that. And then it splits off and goes this way and then that way.
And so we know that okay, so we know the diameter of the jet. It's 100 millimeters. We know that its velocity, this is point C here, this is point A, this is point B. This angle is 45 degrees. Yeah, so the velocity of C is 4 meters per second. I guess you could say this is diameter of C. And then we want to find QA and QB. And we know that the tangential force on plate is 0. And then we have this hint here. We have a hint that says that ZA equals ZB equals ZC. And we want to use the Bernoulli equation to find the velocity of B and A. That was a typo there. So
Well, he might have fixed it for you.
He fixed
This-
it for us.
he probably-
We
this
were
is just-
solving for B and A. It was B and A on our sheet.
Yeah.
Is it really B and C? Well, I was doing it for B and A the whole time. Because I mean, like, what's the point of finding, like, the rules, the velocity? Wait, no, it was. Motherfucker, I wrote some shit on that whiteboard.
was it B?
It was, yeah, it was B and C,
It was
and
B
I
and
was
C.
confused on how we were supposed to find A, because everything else made sense, like rotating your axes and all that, but like, I just couldn't understand how we were gonna find A.
Yeah, because
Mm-hmm.
Nice. Yeah, you better. Good kid.
Spider-Man reflexes. Good. Okay, so yeah, that was a typo there. But you find the velocities of B and A with Bernoulli. Man, I remember going through circuits at my school, and the professor would give us problems with solutions, and they were just riddled with errors, just all over the place. And he would just be like, "Yeah, I mean, just figure it out," you know. And so I was so confused through circuits all the time. Yeah.
Almost
Okay.
the textbooks are like that here too.
Really?
Yeah, like a lot of the textbooks, it'll just be like answer, no solution, and then the answer is wrong.
Mm.
But everyone else on the internet does it wrong also, so they can get the wrong answer.
So to explain the reasoning for this one, in this one we're dealing with forces, right? So we're not simply just dealing with like a mass leaving a system or something like that, because we've got these. It talks about forces here, and yeah. So I guess that kind of like discussion should tell you that maybe conservation of momentum is more applicable in this case. And so conservation of momentum, we have sum of forces is equal to ddt integral over the control volume of rho velocity d volume plus the sum of outgoing mi vi minus the sum of the incoming mi vi, where our outgoings are going to be A and B, and the incoming is C, point C, I should say. And so the trick to this one is we want to take this direction as our like positive x, the tangential direction, because since we have this assumption that the force on a plate in the tangential direction is 0, then by summing forces in that direction, we can just set equal to 0, simplify things. So that's the trick to this one, is that it's like gives you a simplifying assumption. And then because it's steady, then this is 0. I don't think I wrote that down earlier. Yeah, right here, steady. So then that ddt term goes to 0. So what we're left with is that 0 is equal to m dot, and so I'll write m dot a. This is VA, the vector VA, so no direction yet, just the vector. And then plus m dot b VB minus m dot c vector VC. Does that make sense? How did the signs there? Yeah.
Right.
Oh, when you did it opposite? Yeah, and that won't affect anything. It's just however you decide to define it. So, yeah, that's that guy. That's that guy. Okay. So then, if we actually plug in our velocities with some direction assigned to them, we can say this is m dot a. VA, if you look at the diagram, is going to be in the positive direction. And then, but VB will be in the negative direction. And then we have VC, which if you think of VC as like here, then the component that's tangential. That's your question? Yeah. Yeah, so exactly. It'll be negative, and it's going to be negative VC cosine 45 degrees to get the tangential component. So, okay. So then we will end up with, rearrange this a little bit, m dot a VA, that m dot c and the VC are going to go positive, right, because of two negatives. So this is plus m dot c VC cosine 45 degrees, and then minus m dot b VB. Okay. So what we can do at this point is we can say that all the m dots will have a row in them, right? And water will have consistent density. So we can cancel densities here. So we can say that 0 is going to be, since, let me do this. Since we know that m dot equals q times rho, then we can say that this is going to be QA VA plus QC VC cosine 45 degrees minus QB VB. And then we want to know what these velocities are. So the way that he does the velocities is by applying the Bernoulli equation, going back to that hint from earlier. Bernoulli equation, which is going to state that VA, or maybe I'll write like generic, V1 over 2G, that's V squared, plus P1, pressure 1 over rho G, plus Z1 equals to V2 squared over 2G plus P2 over rho G plus Z2. So then we know from the assumption that there's no height differences that those will cancel. And then because this whole system is atmospheric pressure, then we know the pressures can cancel, the whole term there. And then we know, and density is the same too, right? So density and pressure is the same, so those cancel. And then we know that these will cancel. So what you end up with is V1 squared. V1 squared equals V2 squared. So then V1 equals V2. So what we gain from that is that when you look at the diagram, you can say that VC equals VA and VC equals VB. So all the velocities are the same. So VC is going to be equal to V. So like that. Okay, so if we know that, going back to our equation here with the Q's, then we can say that those velocities cancel. And the justification is over here. Okay. So then that will leave us with 0 is equal to, oh no, Q, yeah, QA plus QC cosine 45 degrees minus QB. Okay. And then we can say that if we just rearrange this, we can say that QA minus QB is equal to negative QC cosine 45 degrees. And then we know that QC is VC times AC. So this gives us QA minus QB equals to negative 4 meters per second times pi over 4, 0.1 meters squared cosine 45 degrees. Okay. And then we have one equation, two unknowns, but we want to have two equations for two unknowns. So the second one will be conservation of mass. You can apply that here as well to get that second equation. And so looking here, this is just the, I guess, the intuitive way of doing it. Just thinking like that the m dot from C has to equal the m dot A and m dot B together, right? You could also derive it. Oh yeah, what's up?
I was going to ask that for the velocity.
Uh-huh.
How you said V is C or V A is equal to V and this is equal to V. Or I said that backwards. But
Yeah, this right here.
so it wouldn't be the sum of the two. It wouldn't be VC is equal to V plus VA. That's only when it's mass. Only when we're dealing with mass flow rate. That is like that.
Right. So what this is saying is that the like think about like if two cars were taking an exit, even though like when they split off from each other, they're both going the same rate, but the mass of cars on the interstate has just decreased. So that's kind of how I think about it.
That was a great example.
No, you're good. What's up?
I can figure it out.
Sometimes you just have to say those first words and it just like clicks.
Like, no more speaking for you.
I'm gonna finish this out, but it is 7 in case y'all want to leave or have somewhere to be. But
I'll say the answer. I was like, oh, yeah, no.
the answer is 7. All right. Class is dismissed. Okay. So, okay, where was I here? Yes. Oh, yeah, the second equation. That's right. Okay, so yeah, m dot c, and you could derive this, right, using the formal integral equation. Yeah, or you could just say like this. Okay, so if we take this as like our first equation, and this is our second equation, where we know that m dot c is going to be, you could rewrite this, right, as qc equals qa plus qb by canceling row, cancel densities. So then, and we know QC is that same quantity of 4 meters per second times pi over 4, 0.1 meters squared. That's our second equation in terms of Q instead of m dot. So then we can solve. You could do this by substitution, I guess, elimination, however you want. The way he does it is he just adds them because he sees that there's a negative QB and a positive QB. So when you add those, you'll get that 2 times QA is equal to 4 meters per second times pi over 4 0.1 meters squared times 1 minus cosine of 45 degrees. So I just, yeah, added them and then pulled out the common term and was left with that. And so that will give you QA equals to 0.0046 meters cubed per second. And then, so that's one answer. Oh no. I don't know why it doesn't like my palm as soon as it gets down there.
A teacher that wore a glove.
Really?
That, yeah, he had like a glove that he would wear that was like made for the side of his hand so he could like rest it on it and write.
That's actually super smart because it.
Yeah, it was cool.
That's a neat idea.
Yeah, they just funny to watch him walk around with one glove. It was really tiring.
Like an archer
Yeah,
or something like that. So then we have this plus QB. It says QA plus QB equals to QC, which is meters squared. All right. And then that is going to give you that QB equals to 0.0268 meters cubed per second.
That makes a lot more sense.
Does it?
The problem already made
Cool.
more sense as soon as you said that it was A instead of C.
That does help. That does help. Yeah.
I was literally sitting there, like I made like the initial connection, like rotated the thing, and then I was like, "What do we do for the top?"
I was taking my math exam last week, and like 15 minutes in, Dr. Lusk gets up there. He's like, "Hey, so this is supposed to be a negative, and like it just won't work if you don't have that negative there." So want to make sure they change that real quick. Otherwise, it's not solvable.
He's so funny.
He is cool.
He's like
Yeah,
such
he's
a
cool.
like casual professor.
Mhm.
We have them for Ken and Downing, and it's like.
Yeah.
all the equations have a bunch of imaginary numbers, and the person will be like, isn't this supposed to be an eye? You're like, yeah, it's supposed to be eyes everywhere.
And then he'll look at us and be like, yeah, I forgot it.
That's awesome.
You wanna know what else is on?
Yeah. Oh, that's cool.
That's my cat. Look at this. Ready?
Is that live?
Yeah, watch this. Ready? Batman.
His name is Batman.
Batman. Isn't that sick? He's tripping out. He looks like a little demon.
Oh, that's cool.
Yeah.
He's like, what is
I got an
this?
orange one too, and they like battle on there. So
Really? What's the orange one's name?
cheese it.
Oh, I was hoping it would be like Robin. Cheese it. I like that. Cheese it's good. That's a good name.
Missed opportunity.
Do you all have pets? Yeah. What do you have?
I have a cat.
Nice.
Oh yeah.
Nice.
How are you, Markley?
Named Robin? Maybe.
Family dog. That's what's up. What breed? Mutt or? Oh, nice. My sister has a blue nose, blue cat. Little purple fistula. They're retarded.
Let's see. Record.
So you come here often?
Once a week.
Yeah, even better. We haven't worked out in a week.
I'm going.